Hey everyone, thanks for attending. So a lot of us know that performance is hard, and it really isn't easy on any platform. There's been a ton of literature and discussions of how to make your shaders faster, how to write better game engine pipelines for decades on a lot of different platforms. But this is especially true in VR and XR, mostly because of the pixel bandwidth that these platforms push. You're rendering two eyes, not one. You're rendering at 90 hertz often, not 30 or 60. And most of all, the actual screen resolution and the resolution that your app has to render at to actually achieve a high pixels per degree, which is pretty much perceived resolution, is way higher in VR than pretty much any other platform. So it's no surprise that you devs view performance as one of the most important and maybe hardest parts of even shipping to our platform, Quest, in the first place. But thankfully, we made a pretty sizable dent in this substantial problem pretty recently. Qualcomm made a step function improvement in GPU performance in their XR2 Gen 2 platform, which is in our Meta Quest 3. And the most substantial improvement was in GPU, even though CPU and memory were really upgraded as well, all culminating in a 2.6x improvement over our predecessor, the Meta Quest 2. And that really spawns an important question, which has honestly created a fair amount of dialogue in the past few months, which is exactly what can you do in the new device that you couldn't do previously? Yes, we know it's 2.6x faster, but the answer is definitely not going to be linear, that pretty much every effect is 2.6x better. There's definitely going to be some effects that work better in the hardware than others, and that's what we're excited to share in today's presentation. So as a quick agenda, we're first going to discuss exactly how to utilize the new GPU with a lot of specific case studies. Then we're going to go through exactly what is fast now and maybe what might not be as fast despite the advancements. Then my Qualcomm colleague Rodrigo is going to discuss the Snapdragon Game Toolkit and round us off with the discussion about the Snapdragon developer tools. And as a quick intro, I'm Neel Bedekar, and I'm a tech lead manager at Meta, whose team is pretty much focused on driving developers, graphics, and performance at a lot of different layers of the stack, often Unity, Unreal, as well as the graphics driver in close collaboration with Qualcomm. And I'm really excited to be joined by Rodrigo, staff rendering engineer at Qualcomm. So let's first start by analyzing the types of rendering work that an app in Quest 2 traditionally would do. And now's a good time to mention that we at Meta and Qualcomm have very historically told you specific types of recommendations of your render passes. Put simply, it's that you should always stay single pass. And on other platforms, you're often used to multiple render passes, whether that be a shadow prepass, even a Z prepass, a whole bevy of post-process effects. And in our platform, we've told you, render everything in one main pass, all of your draws in a forward renderer right there. Now, why is that? The answer is pretty simple. It has to do with the GPU architecture. Pretty much the idea that the texture memory on this GPU, the Qualcomm GPU, that it's held true in all of this mobile series, but especially in our XR2 platform, is that the texture memory resides off the GPU, and it's extremely slow to access, to read and write from. This is in stark contrast to PCs or consoles, which often have like gigabytes of VRAM, which are co-located in the GPU. And that's why a lot of your render pipelines have to adjust as a result. For example, post-effects passes traditionally are going to read and write to this memory very often. A bloom pass is going to generate MIP chains that need to be written into this memory and sampled from in every one of these passes. Now, the good news is that the architecture of this GPU has always been this tiled render in a mobile platform who's entirely built to work around this by minimizing this memory bandwidth as much as possible. So a theme that we're going to see is that a lot of what's going to be fast in the Quest 3 and this new hardware is still going to be exploiting properties of a tiled render. It's going to be minimizing this memory bandwidth movement as much as possible. So now we're going to find out whether or not it's still a good idea to adhere to one main pass. Because with this massively expanded Quest 3 budget, there's now a ton of additional headroom. And what should we start to use it on? If we do pretty much nothing special, we'll probably end up with the bottom image. You'll notice it's a little larger, the main pass, than the top image, and that's just because we assumed resolution is going to be a little higher. But there's a lot more we can do, and one option is to just scale up the main pass itself. And honestly, we still think this is the best option. There's a ton of things that you can do to increase the cost and visual quality of your main pass. Maybe the best one is material complexity. a lot of your apps, not only do they use one single main pass in Quest 2, but they probably had slightly more simplified materials. And now we'd recommend leaning into maybe materials that use techniques like physically based shading, which are going to add a lot more texture samples, a lot more ALU computations in the shaders. But the new GPU is probably a really good fit for that. There's a lot of other things you can do to scale up the main pass, which we listed out below. Like texture quality is a big one, higher res textures, higher quality texture sampling, like anisotropic filtering, and increasing draw distance to just render more objects. All of these are really good options, and most of all, it does fit with what the hardware is really good at. It exploits this principle of a tiled renderer because you're still only really transferring memory from this like slow system memory region to do things like sample textures, and once at the very end after your main pass is done. You're not necessarily introducing a lot more memory bandwidth. So this is a really good option. And this is a quick video from Red Matter 2, one of our most visually appealing devs in the Quest platform. It's a before and after video. Try and notice. The change they made was to change their texture sampling from trilinear to 8x anisotropic filtering, and the visual quality difference is pretty stunning here. Now let's start looking at injecting a few passes in there, which are also pretty good options. And the next question would be, should we consider a prepass? Well, the answer is kind of, because there really are many different types of prepasses. Not all of them are equal. And really quickly, to recap what a prepass is, a lot of rendering techniques historically in other platforms have often required you to render a prepass with all of your geometry. And that means duplicating all your draw calls, but often you only bind a vertex shader, which is really cheap. You don't have this per pixel expensive light computation. And you can also simplify the vertex shader to only output position, which is really good. The vertex inputs only need to be position per vertex. You don't need a lot of extra data like normals, UVs, et cetera. So that's pretty much what a prepass is. And there's a few types of approaches. One would be a Z prepass, which a lot of rendering techniques and other platforms have used to often eliminate overdraw, being one of the use cases. We're actually going to mention it's ill-advised on this hardware, specifically because the Z prepass, the main goal of it is to reduce overdraw, but the Qualcomm hardware has something known as LRZ. We've talked about it a little bit in past Meta Connect sessions and whatnot, but there's a lot of reading on Qualcomm's documentation online that you can check out here. The point is you probably don't want to spend that like 2 milliseconds GPU on a large Z prepass duplicating your draws. But a shadow pass, on the other hand, dynamic shadows, this could be a really good fit. And the main reason is that dynamic shadows could actually contribute really heavily to the visual quality of your app. What the shadow mapping pretty much does is it uses a prepass to render a shadow map essentially from like one main lights perspective, and then utilize it when you're actually like rendering your main pass. So here's a quick overview of what really good dynamic shadows look like. This is also from Red Matter 2, and notice how on the player's character you're seeing a lot of dynamic shadows. They actually used a pretty expensive shadow anti-aliasing technique known as PCF, percentage closest filter, and they actually used a 5x5 kernel, which is pretty expensive. So that's why you can see such a high quality shadow resolution there. Now, the quick verdict in the shadow pass is that the shadow map generation is actually a pretty good fit for this hardware. If you think about what it's doing a lot of these draw calls, but as we just said, that's still using the tiled render. If you have a 500 draw call scene, yes, you're going to add 500 more draws to render that shadow map, but they're probably going to be really cheap. They're not really pushing too much memory bandwidth. So that part's probably pretty good in this new hardware. The shadow map usage is a little bit slower. Because it does have a lot of texture sampling. We just saw the 5x5 kernel, but it's probably still pretty viable, and we would recommend it if you have the performance budget. Now for the prototypical question, is post-processing fast? And this has become a real debate. It's almost turned into our platform's version of can it run Doom? Because it's like, can it do XYZ, insert XYZ post-pass? Is it fast now? Well, the answer is kind of yes or no. So there's fast post-processing, and then there's slightly less fast PP. And the Vulkan subpass system is a technique that allows a post-pass to sample from the main pass, which you just rendered to, the main color output, without actually reading or writing to and from system memory, which we just said is the memory bandwidth that you're trying to avoid. So this enables a bevy of effects. A tone mapper is a great example. A lot of you tech artists, you've always assumed that you have a tone mapper on your platform. HDR is a pretty good example as well. Color grading as well. This has been supported in UE5 for a long time, and our graphics integrations and Unity support is a very core priority. We hope to land it really soon. And the video on the right really quickly demonstrates this. We'll just go through it for a few seconds. A tone mapper can be used for things like day and night cycles, as well as a lot of different effects. So fast processing, really good because it exploits what the hardware is. It almost avoids what the hardware is bad at, the memory bandwidth transfers. Then there's, frankly, less fast post-processing, which is effects that are just incurring so much of that memory bandwidth. And a good example is Bloom, which is a post-processing technique that a lot of you devs have probably wanted to use in different platforms. And we are trying to improve support for these like less fast post-processing on our platform. We're shipping per-pass foveation both in Unity and Unreal. The idea is we know what foveated rendering is. It can make your main pass faster. You can apply the exact same principle to post-processing passes like that Bloom pass, and you'll see like a 10-15% GPU win. So it's a pretty good idea. And we are exploring mobile HDR support on Unreal. And for Unreal Engine developers, you'll know that all these post passes are gated behind mobile HDR support. So we are pretty much looking at those as well. So the quick verdict with post-processing is that there's faster and then there's less fast. And the faster, the sub-pass-based post effects like tone mapping, it's going to be a great fit for not just this hardware, but frankly for the Quest 2. Now the non-sub-pass post effects, we need to be clear. It's not exploiting anything that the new hardware is particularly good at. It's incurring a ton of memory bandwidth, which is almost what the new hardware is not good at, but it still could work because you have such a larger GPU budget. When you scale up by 2.6x, you now are going to find yourselves with a budget that so much headroom that you didn't have previously to play with. So our recommendation is basically that's going to be pretty expensive, but it could definitely still work for your content budget, and it's all a trade-off at that point. The main theme we really want to drive home is that one size does not fit all for how to utilize this GPU improvement. You can scale up resolution. The Red Matter 2 case, which we mentioned earlier, those developers are rendering somewhere at like 3K by 3K iBuffer resolution, which is like a scaling factor of 2.5x, dramatic visual quality improvement, and that's a pretty good way to use it. You can increase material quality, having physically based shading, type materials, and then you can inject pre and post passes if you find that it fits with your content budget. So there's really many ways to skin this cat, and it's up to you to figure out the best one. And what we'll pretty much leave you with on my end is a framework for determining is a given rendering effect really a good fit. You want to sort of consider the memory bandwidth being pushed of that effect and try and ask yourself, is it different than the memory bandwidth if you were trying to render that effect on a different platform? With Vulkan subpasses, specifically in that tone mapping or HDR case, the answer is yes, because what would happen in PC or console is you'd render your main pass, you would write each draw out to VRAM, then you do the tone mapper reading sampling from VRAM, you write it out to VRAM again when the tone map pass was done, and now you're eliminating so much memory bandwidth. You're only doing the texture sample. You're only essentially doing one texture right out at the very end, and if you could count how much memory bandwidth you're pushing on PC versus on our platform, it would be way lower, and that's why the answer is definitely yes. It's a good fit. Something like increasing draw distance and scaling up your main pass is probably also a really good fit because, again, it's exploiting the concept of a tiled render. If you have like 300 draws and now you have 500 draw calls, every draw call it's not writing to system memory until that render pass is over. So that's a really good fit. A lot of post-processing effects like Bloom, they're not like truly customized to our platform. They're not explicitly a good fit because they aren't incurring a lot of that memory bandwidth. But you can still use it if it fits in your budget, and it very well might. So with that, I'm excited to hand it off to my Qualcomm colleague, Rodrigo, to discuss the Snapdragon Game Toolkit, as well as a few other tooling wins.
Hi, everyone. My name is Rodrigo. I work with game developers like most of you here today, and I'm really excited to show and talk a little bit about our tools, our platform, and what we can offer for developers. We are in-house game studio at Qualcomm, focused on creating and developing state-of-the-art technology to everyone. Today I will go over one of the areas that I find that is essential for everyone who is doing game development, especially if you are going from a PC console architecture to a tiled one like Adreno. There are lots of problems and difference between such platforms, and I think it's crucial to pass a very good understanding how super resolution works on our platform. Let's talk about it, how Meta and Qualcomm are helping developers with it. So we still feel that even though super resolution is very discussed nowadays, developers see it as a bad thing. Imagine this, you are working on a part of a game, like you are almost hitting 90 FPS, which is a good average for a VR game. No shadows, maybe low lights, a couple of post-processing passes. Like the game doesn't look good, you know that, and you tried all optimizations possible. It's very likely that upscaler would be a good fit for this and would allow you to get that extra frame time to add those passes that you had to remove or even boost the existing ones. That's one of the reasons why we developed the Snapdragon Game Super Resolution. It was tailored for Adreno GPUs. It's literally very light, barely no dependencies, just one input texture color. And we see excellent feedback from many developers. A couple examples, we have the Figmin XR and the Virtual Desktop, both implemented as GSR, and they've seen a very big increase on streaming performance. Also important to say that you're not limited from using super resolution, doing upscaling only on the final scene color. Nothing prevents you from doing that on intermediate passes, especially like if you're talking about expensive one like shadow generation. Also, you might think that, okay, I'm sold on that, I want to use super resolution. How do I go from there? Like, it's probably a lot of work to get that added to my application. Well, Qualcomm and Meta partnership allowed the creation of the MetaQuest Super Resolution. It was built on top of GSR and added directly into the VR compositor. It's there for you with just a single press of a button, no excuses to not try it out. It can be activated by using the composition layer settings. If you're using Unity, it's on the OVR manager. If you're using Real, it's on the player start object on the rendering section. For the ones venturing using a deferred renderer, we will be soon releasing the Snapdragon Game Super Resolution 2.0. It's our take on a temporal upscaler solution. Not much to share today, but keep an eye on our forums and blog posts for more information about that. Also important to mention that we consistently advocate for improvements, new extensions, and functionalities for Vulkan through the Kronos committee. The multi-view per view extensions were recently released, and they enable dynamic resolution Quest by eliminating unnecessary rendering areas. Okay, now cool. You wanna now know which passes are good candidates for super resolution, or maybe you're still in the early development stages and doing some profile analysis, debugging. How do you go from there? Well, we have an arsenal of tools made for developers, and starting directly with Snapdragon Profiler, it's our main capture tool. It has several options: snapshot, trace mode, runtime mode. And if you're familiar with it, we'll be happy to know that we recently released the CLI version. Also, the Adreno compiler demonstrated over the last year how powerful can be an offline analysis, shader analysis tool. Today, it supports all of our 6th and 7th generation of GPUs. I will be focusing more on SDP and AOC today, but we have a QR code at the end of the presentation. Feel free to look at our developer tools page and get more of our documentation and other tools available to you. But on SDP, so it's not just another profiling tool. It gives you information that is normally not available with other profiling applications. It can, this is a tile platform, right? So you have to deal with things like binning, concurrent binning, GMM loads. Those are much more important, and some of those are only present on Adreno GPUs. And this example here, for example, it was a textured necessary copy texture that was being made and copied to multiple post-processing passes. As soon as we detected that, we removed this unnecessary copy. We saw removal of load operations through the whole set of post-processing operations. So things like these are very important in specific to our platform. So yeah, I really strongly suggest you to read up the documentation and see how you can start using those tools. The CLI form, I'm pretty sure everyone here had to at least once implement a debug menu. Can be like just a FPS counter, maybe some detailed path information. We hope that the CLI version will allow you to, will simplify your lives whenever you need to do this work again in the future. I also talk about integration. I want to address how important and powerful like Adreno Flying compiler is to shorten development cycles. Like normally you have to compile your application, then deploy it to your device, then run it, capture, and then get stats information and all the fun stuff. This way you can basically throw your shader code directly to Adreno Flying compiler, and that's it. You get all the stats. And here are just a couple of them. You have many more. Like the Adreno Flying compiler has been growing over the last year, and it's really like an essential tool, like especially for doing some sort of material editor. If it's like a globe, you can just drop it there. When you're generating your material, you get all the stats and all the information directly. And it will have like an overview of how good it will run for your game or application. Well, you can find more information about our tools and training documents on our tools portal. I hope we were able to give you even more reasons to start developing VR applications today. And yeah, if you have any questions, please feel free to reach out to us after the presentation. And thank you, everyone, for your time. Yeah.
Yeah. Maybe there's time for Q&A right now, and if not, you can definitely find us right outside pretty much here.